Assalamu alaikum, students and friends. Welcome to Circus Physics video tutorial. I will be discussing a problem involving a radio wave emitted in pulses by a weather radar system that illustrates an application of Heisenberg Uncertainty Principle. So join me, stick around, watch and learn. The question is, whether radar systems emit radio waves in pulses. For a typical system, the frequency used is 3.00 gigahertz. That's equivalent to 3.00 billion hertz. And the minimum energy uncertainty of the radio photons is 5.50 times 10 to the negative 29 joules. Question letter A. Find the time duration of each pulse. Question letter B. Find the length of each pulse. Question letter C. Find the energy of an average photon. And question letter D. Find the minimum frequency uncertainty. A typical weather radar system uses a frequency f equals 3.00 gigahertz, or that's equivalent to 3.00 times 10 to the 9 hertz. And the minimum energy uncertainty, delta E, is equal to 5.50 times 10 to the negative 29 joules. Our first target variable is the time duration, denoted by delta T. Right? This is the time duration, delta T, of each pulse. This is the time it takes the radio pulse to emerge from the source. It is also the time uncertainty for an individual photon with or within the pulse, since we do not know when during the pulse that photon emerges. The second target variable is the length of each pulse, denoted by delta x. So delta x is defined as the position uncertainty of the radio photon, or it is the spatial length of the pulse, since a given photon could be found anywhere within the pulse. The next target variable is the energy or average photon energy. We consider only the energy of the average photon, since the energy of each individual photon is uncertain. And our last target variable is the minimum frequency uncertainty, denoted by delta F. Since there is a minimum energy uncertainty, there is also a corresponding minimum frequency uncertainty because the frequency of each individual radio photon varies. Moving on to our calculations. To calculate for the time duration delta t, we use Heisenberg Uncertainty Principle equation for energy and time, which says that delta t multiplied by delta E is greater than or equal to h bar divided by 2. Taking the minimum time duration, we have the delta t equal to h bar divided by twice the delta E, right? Where we define the h bar as the value of the Planck's constant h divided by 2 pi. So substituting, we get the h bar right, equal to 1.055 raised to the negative 34 power joules second. And that will be divided by 2 times the value of delta E, which is 5.50 times 10 to the negative 29 joules. Right? So we get the time duration delta T equal to 9.59 times 10 to the negative 7 seconds, which is relatively a large amount of time as far as the radio pulses are concerned. To compute for the length of each radio pulse, denoted by delta x, right? So the length of each pulse, delta x, is just equal to the speed of light, c, multiplied by the calculated time duration earlier calculated, right? That is, delta x is equal to 3.00 times 10 to the 8 meters per second multiplied by the calculated time duration delta t, which is 9.59 times 10 to the negative 7 seconds. So doing our math, we will get the length of each pulse, delta x, equal to 288 meters. Take note, this delta x should not be mistaken to be the wavelength of a typical radio wave. All right? A typical radio wave has a wavelength that ranges from 2 to 3 meters. For the third target variable, the average photon energy, we use the relation energy is equal to Planck's constant multiplied by the frequency f, all right? Or the average photon energy is equal to 6.626 times 10 to the negative 34 joules second. That is the value of Planck's constant, all right? Multiplied by the given frequency of the radio wave pulse, which is 3.00 times 10 to the ninth power hertz. So again, doing our math, we will get the amount of the average photon energy, E, equal to 1.99 times 10 to the negative 24 joules in three significant figures. Lastly, finding the minimum frequency uncertainty denoted by delta F, we still apply the relation energy is equal to Planck's constant times the frequency, or frequency is equal to energy divided by Planck's constant. All right? Since what we are looking for is the minimum frequency uncertainty, or delta F, so that will become delta F equals delta E divided by Planck's constant, right? Substituting, we get 5.50 times 10 to the negative 29 joules, that's delta E, divided by Planck's constant, 6.626 times 10 to the negative 34 joules second, or that gives us delta F equal to 8.30 times 10 to the fourth power hertz, which when converted to gigahertz, all right, the minimum uncertainty frequency, or delta F, is equal to 8.30 raised to the negative 5 gigahertz. In addition to the four target variables as in the question, we also include the minimum momentum uncertainty, delta p sub x. This is simply equal to h bar, or Planck's constant, over 2 pi divided by twice the minimum position uncertainty, delta x, or 1.055 times 10 to the negative 34 joules second divided by 2 times 288 meters. And doing our math, we get the value of delta p sub x equal to 1.83 times 10 to the negative 37 kilogram meter per second. We also calculate for the average momentum of a photon denoted by p sub x, right? So p sub x is just equal to the average photon energy, capital E, divided by the speed of light, small letter c, or that is 1.99 times 10 to the negative 24 joules divided by 3.00 times 10 to the 8 meters per second, or the photon momentum p sub x equals 6.63 times 10 to the negative 33 kilogram meter per second. So it appears that the minimum momentum uncertainty, delta px, all right, is in fact only 0.0028% of the average photon momentum, right? Delta p sub x, 1.83 times 10 to the negative 37 kilogram meter per second, when divided by the photon momentum p sub x, 6.63 times 10 to the negative 33 kilogram meter per second, and converted to percent, that's just 0.0028%. So once again, we stress that the minimum momentum uncertainty delta p sub x is only 0.0028% of the average photon momentum p sub x. Likewise, when we compare the value of the given minimum energy uncertainty delta E, which is 5.50 times 10 to the negative 29 joules, all right, with our answer in part C, all right, the computed average photon energy equal to 1.99 times 10 to the negative 24 joules, all right, it also comes out that delta E is also 0.0028% of the average photon energy. In other words, both the energy uncertainty and the momentum uncertainty are relatively small for radio wave pulses. All right. For instance, the estimated energy of each radio wave photon could possibly range from 1.99 times 10 to the negative 24 joules plus or minus 0.0028% only. And the estimated photon momentum could also range from 0.0028% below the average or 0.0028% above the average. The reason for this is that the radio wave pulse, all right, is relatively long with its uh, position uncertainty delta x equal to 288 meters. All right. And the other factor is that the time duration of the pulse is relatively long, with delta t being equal to 9.59 times 10 to the negative 7 seconds, which is just actually equal to 0.959 microsecond. So, we can conclude that since both delta x and delta t, all right, the position uncertainty and uh, the delta t are large, relatively large, resulting to small photon energy uncertainty and small minimum momentum uncertainty. All right, so our conclusion earlier that since both delta x and delta t are large, resulting to small photon energy uncertainty and small minimum momentum uncertainty, actually obeys the Heisenberg Uncertainty Principle. All right? So the Heisenberg Uncertainty Principle takes two forms. First, it states that the larger the uncertainty in the time of a physical phenomenon, the smaller the uncertainty in the energy of the phenomenon. So that is summarized in this mathematical expression: delta t times delta E is equal to or greater than h bar divided by 2. And the second form states that the larger the uncertainty in the location of a physical system, the smaller the uncertainty in the momentum of the system, which is also summarized in this simple relation: delta x times delta p is equal to or greater than h bar over 2. And that concludes our tutorial for this topic. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.